Alright, so today we are looking at formal groups as, again here, formal groups over a complete valuation ring. So we're going to let a little bit of setup here. A bit of mess. I messed up a little bit here with my book here. A bit of setup. We let K be a complete ultrametric field. With a valuation ring A at a maximal ideal M. So we're going to let f of x and y be a formal group over A. And we're going to let G be the collection of x1 to xn, with xi being an M, being our maximal ideal, polynomial from all over ones, and we define multiplication on G by our formal group law, of course. And then G is an analytic group. I guess we should write it as a Lie group, don't mind what just happened. So we need associativity. We need a unit, which is going to be 0, and inverse. Phi x as x inverse. Each of which come from the corresponding rule from the formal group by a lemma which states let F be the formal power series over the valuation ring of x1 through xp, and Gi be in a similar valuation ring except with over indeterminates I from 1 to q instead of x from 1 to p. And suppose that G of I of 0, Gi of 0 is 0 for all I. Let H be F on each component of, on each G I, on P GIs which will put them inside the formal power series over y from 1 to q. Then for x1 through xq in M, we have h of x passes on by f to each g, and this is automatic. You can just work through this on your own if you want. And define such a group is called standard. And from that we fall into another theorem. Any analytic group chunk contains a standard open subgroup. And let's verify this. Let G be an analytic group chunk. And we can assume by shrinking G and choosing local coordinates, let G be an open neighborhood of 0 in K to the n, and multiplication in G is given by a power series fxy such that f converges on a ball of radius on d ball of radius less than epsilon. We write f of x and y to be, of course, x plus y plus coefficient c alpha beta times the higher order series x d alpha y beta with the size of alpha being at least 1 and the size of beta being at least 1, and the c sub alpha beta being vectors in k to the n. Then we want to change coordinates by multiplication by some mu in k. So specifically, if we have x and y in G such that z equals xy is defined, we can set x prime to be mu x, y prime to be mu y, z prime to be mu z. Then z prime is x prime plus y prime plus for each coefficient alpha, beta, it's going to get scaled by mu to the alpha, size of alpha plus size of beta minus 1, times of course x prime to the alpha, and y prime to the beta. Giving the new group law f mu coefficients of this, write it in this order so I can make sure I have enough room, of our coefficient C alpha beta over mu to the size of alpha plus the size of beta minus 1. So for large mu, I should write with a large absolute value. We can have the coefficients of f mu in our valuation ring, and that the size of mu times epsilon being at least 1 such that f converges in the unit ball. With the unit ball, a standard subgroup of G. Alright, and this comes with a couple immediate corollaries. I gotta survey how long the next chapter is going to be. It's too long to finish, so I kind of want this video to be shorter anyways, because I need it to be shorter, so we're probably going to do part of the next chapter. Anyways, first corollary, any analytic group chunk is equivalent to a Lie group. Another immediate corollary to end this chapter. Any analytic group chunk has a basis of neighborhoods of the identity consisting of open subgroups. And yeah, it's actually only been like 14 minutes, so we'll get the next chapter started and we'll just cut it off awkwardly some point in there. So next chapter is filtrations on standard groups. And we keep our notation, and we additionally are going to let W from K to the reals, or it can be infinity, the valuation of K that is for some alpha in R, real number strictly between 0 and 1. We have that the absolute value of x is equal to a to the power of this w to the x for all x and k. Then we want to extend this, so for x, split into components x1 to xn and kn, we're going to let the evaluation of our vector x be the infimum over I, the valuation of each component. Then for lambda being at least 0, we can give ourselves just a very natural filtration to give based on the valuation. G lambda, of course, is going to be x in G with a valuation being at least lambda. And of course, we can give ourselves G lambda plus being x in G having a valuation strictly greater than lambda. More generally, for an ideal A of alpha, we let G of alpha be x in G, where xi is in A for all I, so every component is in A. And of course, GA plus being x in G. Being xi, being in A, acting on our maximal ideal, of course, for every coordinate. So if A lambda is defined to be the ideal of elements of A with a size being at least lambda, then G of lambda is G of A of lambda, and likewise for our pluses. G lambda plus is G A lambda plus, which is additionally going to be equal to G of A lambda times M. Alright, so let's work with this a little bit here. Theorem here for all ideals A of A, GA is a normal subgroup of G, and GA plus is a normal subgroup of G. Additionally, if I guess also we have that x being congruent to y mod GA is equivalent to saying that xi is equivalent to yi mod A for all I and for all x, y, and g. In proof, we actually have this directly from previous formulas, but we can go and work through this proof the long way for better illustration. So we're going to let G of A, a evaluation ring over our ideal, be the group systems, x bar being x bar 1 through x bar n, with each xi bar being in M over A, the multiplication given by the reduction F bar of F mod A. Fx is in G, then the reduction X bar of X mod A is defined, of course. Defined as A is an ideal, and the map from X to its reduction is a surjective homomorphism, which we can write as phi of A sending G to G of alpha over A. We note that the kernel of phi alpha is going to be G alpha, which proves our theorem. Done. We're done rather for G alpha, GA with a GA plus falling for free, as we can just rewrite GA plus as G of A times M. Alright. So, now from that we have an immediate corollary, which is the fun part. It's not immediate actually, which is that the subsets G lambda define, as we would expect, a filtration of G. So we need, first off, we need W of 0 to be infinity. Secondly, we need W of x to be positive for all x in G. We need W of x times y inverse to be at least the infimum of Wx and Wy for all x, y in G. And fourth, W of x and y must be at least W of x and Wy. That's the commutator inside, if you do not recall. You probably do though. It's only been like 100 episodes, right? 1 and 2 are automatic. They're by definition of G. And question and option and axiom 3 is equivalent to G lambda being a subgroup of G for all lambda, which we saw is true. And assertion 4 is equivalent to saying that the commutator of G lambda as a whole and G mu as a whole is contained within G of lambda plus mu. If X is in G lambda and Y is in G mu, well, first off, the commutator of X, the bracket of X and Y, is going to be in G lambda plus mu, which is obvious. And secondly, we saw that the commutator of X and Y is congruent to the bracket mod G lambda plus mu positive. Alright, so how far are we through this? Man, I'm gonna end up doing a whole episode, aren't I? No. You know what? I mean, I said I gotta keep this one short, and if I keep going, we're pretty much just going to do a full episode. I think I'll be leaving a full episode for next time here, so I'm gonna call it here. Not where I maybe should be ending off, a bit short, but it's where I'm going to be. Yeah. Thanks for watching.